is a, and I cherry pick. I teach with some other professors, and every once in a while, when I see a particular lecture that they've done that we've recorded that I think is pretty good, I'll cherry pick it and I'll give you a link to it, or I'll edit some parts of it out and stuff like this. This is a lecture from Professor Cassia on study design. That's particularly good.
How we can analyze data.
I'm going to leave that on here for you to view on your own. Right? And I think it'll be pretty informative. Next week, I'll kind of like do a quick review of it rather than spend the next half hours watching this or something like that. Okay, but you have the link to the YouTube recording of it. Oops. Okay, good. I got to get back to. I got to reopen that. Oh no. Okay. Street. Recently closed windows. I think I'm going to have to go back to Blackboard again. Didn't mean to close that. I'm going to go to lab section now. Okay, let's go to session 2. Okay, so getting back to what we were talking about before, graphics and in statistics, and also in the operation of SPSS. We have a couple of exercises here. I'll just show you quickly what they look like. Okay, here's one that that's an old one. I think that's the wrong one. Got another one there. If I can get Word to close. Oh, there we go. Okay. Okay. Let me try this one. Okay. This is a little bit more recent. Okay. And I'm going to use this data set, and we're going to go through this and take a look at creating some charts and some, this actually takes you through it step by step, creating different kind of charts, analyzing different kinds of statistics, using some of the data that you have at hand, using the appropriate commands, choosing the appropriate types of displays and tables, and so on and so forth. And it also goes into doing some basic descriptive statistics. Okay, particularly on quantitative data where you want to find means and medians and so on and so forth, see histograms and so on and so forth. You can go through this step by step on your own. I'm going to freelance a bit, and I'm going to open the data up. I'll probably wind up going through all of this that's on here, but I think I'm a little bit more comfortable freelancing rather than bouncing back and forth from this. Okay, now the data that I'm going to be using is a file called NC Birth. It's North Carolina Birth Statistics. It's a version of it that we modified so that we randomly selected 800 births from all of the births that took place in North Carolina during that particular year. I think it's about 15, 20 years old, this data. And we have various versions of this. You know the .sav version? We know that that is a SPSS data file. We have an Excel version of it. We have a CSV comma delimited version of it, which is what you would use if you were working with R, and so on and so forth. So I'm going to open up the SPSS version of it. I think I have it on a folder here already. Well, perhaps not. Okay. Okay, you can download it to your desktop or to a folder and so on and so forth. You notice what I did there, right? So you guys can work on this when you're in the lab here. I just right-clicked on it or control-click for a Mac, and I said Save Link As so that I can actually take that file and save it to wherever I want. If I want to click desktop, I can save it to desktop. In this case, I put it into a folder that's on my desktop. Okay, and it's going to ask me if I want to replace it. I'm not going to bother with that. I already downloaded it. Okay, so I'm going to open this data set. Now, you'll notice on my computer, for some reason, when I installed SPSS, it didn't register the file type, even though I've tried to correct that a couple of times. Normally, you would be able to double click this. I'm going to give it a try, and it should open up SPSS. In my case, it thinks it's a text file, so it didn't open it up. If that happens, you can also go and you can also, depending on what kind of machine you have, tell it which application to open it with. In my case, I'm not going to bother with that. I'm just going to start up SPSS on my own, and I'll open that file from within SPSS. Okay, we'll twiddle our thumbs here while this starts up. Okay. And again, that unusual, that template window starts up. I'm not going to bother with that. I can't close this blank one because if I do, it'll quit SPSS, just an oddity of the program. I'll say open, data, and then I'll navigate to where the data is. In my case, the data is in a folder on the desktop called week 3. Now, if you're using virtual PC, when this first comes up, I think the folder, if you say file open data, I think the folder that comes up is on the server. It's not on your computer. It's on a server at CUNY. So if you want to work with data files, you have to navigate back up to your computer, down to desktop, down to whatever folder you're going to work with. So that's one of the complications of working with the virtual desktop is that you have to be a little bit careful about where you're putting your files, because when you're done, you want to be able to find them again, right? So it gets a little. The first few times you try and do it, you can find it a little bit complicated. Once you figure it out and can find your way around, it's not so bad. But then you compound that with the difficulty and slowness because you're doing it over the internet. The fact that if you could have an interruption in your internet connection and you're kind of stuck, or the fact that every once in a while it gets a little buggy. I usually try and encourage people to spend the $40 or so, actually buy it for your own machine, because I also think it encourages you to use it more too, and that's the best way to learn it. Okay, so since I'm already looking for SAV files, right, SPSS statistical files, I can see this and appears. If it doesn't appear, you might want to check to make sure that you're looking for the right file type. Okay, so I'm going to double click that, or just click it and say open. It's going to give me that funny message about Unicode, which is basically a newer version of the way that SPSS encodes data. Most of the data files you're going to be working with are perfectly happy with their Unicode. You can just say OK to that. Okay, so there's the data that we're looking at. Again, there's two views we have 3 windows that you might be working with in SPSS. You might be working with the data window. You might be working with, and I'll click behind here, whoops, there. You might be working with the output window, or you might be working with a syntax window. And we know that for now, we're not going to worry about the syntax window because that would involve actually writing your own scripts in order to get SPSS to do some various things. Let me get rid of this silly thing. Not now. Okay. Okay, so let's take a look at what we have here in the way of this data. Okay, so we see that the individual births, the subjects or the patients or the trials are in the rows, right? These boxes represent just numbers or figures or text or so on and so forth, or responses, right? So each response, each value represents a single patient, a single birth. The columns represent the variables. Okay, plurality. Anybody know what plurality means? When we talk about birth. Well, put it this way: what's his name? Amal and George, right? They just had a birth, right? Clooney, right? And how many kids did they have? They had twins. Plurality is number of babies in that birth. So that plurality would have been 2. And you'll see a few 2s or 3s in here if you look carefully, right? So that's the number of babies that were born. Sex, obviously, they don't mean the sex of the mother because we know what that is, right? That's the sex of the infant. M age is the mother's age. Weeks is the number of weeks of gestation. And marital is marital status. Now, notice that when we look at this data, we go across here in this data, there's many different forms of data. First of all, gender for the child is male or female. That's a nominal data. The mother's age, that's numerical data. We can see we can almost see that it's in years. Number of weeks of gestation, numerical data. You'll notice that for the most part, SPSS gets it right just by inspecting the data. Notice they saw these three little balls here. That's for nominal data, right? It got it right for gender. Didn't get it right for plurality, because plurality is mostly ones. And it thought, oh, maybe that represents that number represents something else, right? It didn't get it right for weeks because they're relatively small. They're all integers, relatively small numbers. It got it right for marital status, right, and so on and so forth. Got it right for the weight of the infant at birth. Excuse me, I'm still getting over this cold. So it got it right for a lot of stuff, but not everything. Excuse me. So I'm going to go into the variable view. There's a couple of ways I can get there. It's the same window, but it's a different view. One way I can get there is to go up here to view. Excuse me. Go up here to view and switch down here to variables, and the window will change. Right? If I want to go back, view. Notice that where it said variables now is data, because you're in the variable view, so the only place to go is to the data view. The other way I can get there is by clicking on this tab at the bottom. Depending on the version that you have, you may not see a tab down there. So I'm going to go to the variable. Now in this case, each row represents a variable. So each row represents a column in the data view. So plurality, that we saw that was the first column. That's a numeric variable, right? It's a number. Now someone has gone through this data, me, and oops, someone has gone through this data, and they've actually created labels. Okay, when you input or put data in initially, you're going to be giving it a variable name like plurality, age. Age, not very descriptive way of describing mother's age, right? But we can't have spaces or special characters in the variable name. So what we do instead is for plurality, we say, let's give it the label that's more descriptive, number of children born of the pregnancy. So now, anytime we create a table, instead of using the term plurality, it's going to use a label that's more descriptive, number of children. Instead of using the variable name age, it's going to substitute for it the age of the mother, okay, in years, and so on. Okay, so if I look in here, I also notice that for sex, for gender, of the sex of the child, obviously, right? It allows me for those kind of variables, for nominal variables, it allows me to put in values to let us know what those numbers represent. So in this case, if I click on that, you'll notice that it's been pre-coded that 1 represents male and 2 represent female infants, right? So how did that get created? Literally after the data was in, based on the code book, what we know that the original coder, the original enter of this data, how they coded it. Well, they coded it that 1 is equal to male, 2 is equal to female. If I didn't know and I wanted to have that in here as well as another variable, I could say unknown. And I can click add, and it'd be added as another value that might show up in this. I'm going to remove that since it doesn't actually exist here. Okay, but so this coding is something that you would do when you put the data in originally. Okay, so let me just clear up a couple of things here. So gender as nominal, plurality is numeric. Weeks of gestation is scalar, that's numeric. Scalar, SPSS refers to numeric variables as scalar. Weeks of gestation, scalar. Marital status is nominal. Take a quick look there. 1 is married, 2 represents not married. Okay, and race of the mother is nominal variable, so on and so forth. So I'm going to leave it like this for now. I think I got enough variables to work with at this stage. Okay, I'm going to go back to the data view. Okay, so let's try and do some interesting stuff with this. Let's see if in North Carolina they have more female births than they have male births. Right? Let's get an idea. Let's count. how many female births there are in these 800, how many male births that there are on these 800. So it's nominal data. So when we're dealing with nominal data, I'm going to go up to analyze. Almost always we're going to start our analysis or our calculations with that in that analysis tab, right? So that's a descriptive statistic, the number of females or males that are born in a sample or in a population. So if we're counting for a categorical variable, nominal variable, we're actually looking for the frequencies. Number time the number 1 for male, number time number 2 for female comes up. So I'm going to click here on frequencies, okay? And I'm going to get a box that comes up. Now, when we did this the first session, I'll tell you where we are in a second. When we did this in the first session, right, there was only one variable in here, right? So it's pretty clear that you just click on that, move it over to the other box. The whole reason for these two boxes now are obvious, and that is that it wants to know, well, which of these variables do you want me to do this work for? So I'm going to say gender, sex of the child, move that over here. Actually, if I hover, it'll actually show me the whole variable name. It'll show me both the variable name and the label. Okay, so that'll help you out sometime later on when you want to do this. You can't make these windows wider or narrower. There are some things in SPSS that are very developed, and other things that a lot of other programs have that aren't so well developed. Okay, so we're interested in the gender of the child. So I'm going to click on statistics just to look at that. One of the mysteries of SPSS is that it knows that this is categorical data. And categorical data, we're not interested in quartiles, mean, median. So why this is even available here, I don't know. So I'm going to put that away. Now, as far as charts is concerned, I might be interested in getting a bar chart of this data, because bar chart will show you like males, females, right? Those are your home when I'm doing my moving my hands up and down to symbolize a bar is going, 2 bars going up and down. Okay, or maybe a pie chart. Now, I hate pie charts. All statisticians should hate pie charts. I'm going to make a pie chart of this. Well, no, I'm going to stick with a bar chart. I'll go back and make a pie chart. Now, histogram's not relevant here, right? Because a histogram we use for numerical data, right? It's not. We don't use bar charts. We use bar charts for nominal data, histograms for numerical data. So I'm going to click. Now, there's 2 ways I could get it to display this bar chart. One is by frequencies, and one is by percentages. In other words, the y-axis can be described with numbers, or it can be described with percentages of the total. Okay, so I'm going to leave it frequencies and numbers for now. So I'm going to go ahead. I'm going to ignore these others for now, and I'm going to go ahead and say OK. So when I click OK, what's going to happen is SPSS is going to pull the output window up to the front, and it's going to do these calculations. And while that's working, what's happening here is that there are only 2 of us here when we started. So I mean 2, just the 2 of us. So I wasn't showing you about it. So we were viewing it on the screen instead of projecting it to the back here. If you're able to log on. I can't log on. I think I logged you on right before. Yeah. Okay, why don't you come back around here? And what I'm going to do is I'll log you on, so that we have at least 2 computers working. Actually, I might be able to log. Can you get onto Blackboard? No, you can't get onto Blackboard. You can't get onto the system, but you can get onto Blackboard. Yeah. Why don't you come to this side, so that we can work together? Okay. Yeah, I at the beginning here, there's just me, so I thought like I could get away with that without projecting it back there. But I think when I take a break, I'll project it on the big screen so that we can all see it, or you can continue to work on the screens if you want. Okay, so twins, yeah, there you go. I'm not ignoring you guys online. It's just I glance away every once in a while, so I can get a chance to. So somebody's a celebrity hound on here knows that they had Amal and George had twins. Yeah. So at any rate, we're talking about the definition of the word plurality. Okay, so here we go. Because I chose frequency, it shows that in this study there were more male babies born than female babies in this random sample of 800 births in North Carolina in 2005 or something like that. Can anybody tell me, is that correct? Are there more males or female babies born? More females? Oh, so that's an unusual result. There we go. We have a disagreement now. The data suggests, at least in North Carolina for that year, right? Now we don't know the exact number because we didn't count every birth. Now, as it happens, this is one of those rare situations where it's possible to know the true proportion of males and females because they record every birth, right? So you ask somebody somewhere on some computer, there is all the births for that year for North Carolina summarized, right? This is just a sample of 800 random sample of 800 births from that data, right? But if we didn't have that available, right, then our best guess based on what we determine with our random sample is that there's a higher rate of male births than there is female births. More males are born, babies are born than female babies. Whether that's true or not, I don't know. And we could actually calculate, there's a difference between them. But now, is that difference due to chance because it's a sample? Or is it a difference that it really indicates that there's a difference in the rate of male births and female births? Well, you want to know something? With a sample, we'll never know for sure. Even if there's a big difference, we'll never know for absolutely certain. However, one of the important things that we're going to learn about statistics is while we may not be able to say for certain whether or not this trend is true, we will be able to quantify our level of certainty. Like, in other words, I will be able to say, I'm 95% sure this is right, or I'm 99% sure this is right, or I'm only 50% sure this is right. Now, as it happens, we're going to set thresholds for ourselves. We're going to talk about that as we go on in the semester, this idea of alpha error and beta error. Alpha error is a type of error where you make a prediction and it turns out to be wrong, right? That's a bad thing. We're going to talk about that later on. So, in general, you're willing to take the leap and say that, in this case, for instance, you would be willing to take a leap and say that more males than female babies are born in North Carolina if you can say it with 95% certainty. In other words, less than 5% chance of being wrong if you say that, right? So that's where you're going to start. You've probably seen alpha is equal to 0.05 for this study and so on and so forth. That's where that comes from. But as we move forward, you're going to get better and better understanding of the fact that we're never going to say anything certain, but we're always going to at least qualify our prediction by telling people what our level of certainty is, right? As opposed to just saying it's true or not true. Okay, so that's really where we're going here. Okay, so we got two things here. We have a table which summarizes this data, and we have a chart which summarizes this data. Again, you look at the chart, it's pretty. You look at the table, you have to read the thing and interpret it, right? You look at the chart, you immediately see what the difference is. I just wanted to show you that now. If I go back to analyze descriptive statistics frequency, it keeps all the data and the information and the choices that you made. It preserves those. I'm going to go back at the charts here, except this time I'll do it by. I'll do part charts and I'll change it to by percentages, just so you can get another look at this. There you go, males and females. And it didn't put the numbers in. There's a way, there's a way to get numbers. It's just rather than play around with this, I wanted to get into this at another time, editing the charts and graphs in SPSS. But for the time being, I'm just going to go back and do it as a bar chart again with percentages. And on the side, on the y-axis, it should show up as percentages. See if don't make a liar out of me now. There you go. Here's percentages. 53% of the births are males. 48% of them are females. Right? Change the axes for it. Okay. So now let's take another look at this. Let's take a look at how we might handle numeric data, which is in a lot of ways a lot more complicated to describe than categorical data. And by the way, before I go off of this, let's analyze. Let's use a more complicated nominal data. Okay, for instance, let's look at, we have ethnicity in here. Ethnicity. Let's look at the data by ethnicity. Again, ethnicity is a categorical variable. I didn't show it to you in the variable view, but ethnicity may have 5 or 6 or 7 or 8 or 9 values, right? So it's going to look a little bit more complicated. I'm going to click on charts. I'll still make a bar chart up. I'm going to leave it as percentages. I'll click continue, and let's see what kind of tables and charts we get now. Okay, so here, non-Hispanic white, non-Hispanic black, Hispanic, other. I guess it wasn't as complicated as I thought it was. Is there another variable there? Analyze descriptive statistic frequencies. Besides ethnicity, race of the mother. Okay, let's try that one. I think that might be a manufactured variable that we are going to use later on for demonstrating some other stuff. So let's go back to race of the mother. Where did I lose that now? Yeah, race of the mother. This should come out a little bit more complicated. Okay, but here we go. Okay, now here, white, black, American Indian, Chinese, Filipino, other Asian or Pacific Islander, and so on and so forth. And here's the distribution in this population by race. Okay, and again, this happens to be North Carolina. I don't, again, it's a kind of a kludge data set. It's only 800 out of a really big data set. I don't remember how careful we were about making sure it was random or not. But so nice thing about these data sets is these results is that we can go in here, we can edit this. You can change the color of the bars. You can do a whole bunch of stuff. Bar options, columns, clusters. Okay, count bar options. Where's color? I just installed this version of SPSS, and I haven't had a chance to really go through it and kind of like tune it up. Just give me color. No, that's the background. Oh, I'm sorry I did that now. Okay, but you can see you can change a lot of things, background, titling, and so on and so forth, text, text fonts, and so on and so forth. But there's an editing function in here. So I'm going to go now, and I'm going to take a look at numerical data instead. So I'm going to go up to Analyze, Descriptive Statistics. This time, instead of frequencies, which we usually reserve for categorical and nominal data, I'm going to go into descriptives. And you'll notice that I got a number of other options down here besides this. The two that we're going to look at tonight are descriptives and explore. Descriptives is a scaled down version of explore. So I'm going to click on descriptives. And now I want to work with numerical data. Okay, so how about the age of the mother? So let's take a look at these 800 women. Okay, now what might I be interested in knowing about the age of the mothers? Usually we want to know where the center is, the mean, the median, the mode, and so on and so forth. And we want to know what the variability is, what the youngest is, the oldest is, how spread out they are. We want to know standard deviation because that's our measure of variability. So I'm going to go into options. And let's see, it's already checked off for mean, standard deviation, minimum, maximum. I'm going to check off variance. What's the relationship between variance and standard deviation? You guys remember we did that in Excel last Monday.
The variability and standard deviation.
Exactly. The way we calculated the standard deviation is we took the variance, found the square root of it. So if I know either one of these, I know the other. But I'm going to, SPS is going to help me out on this. I'm going to check range also, and I'm going to say continue. So a little thing there said standard error of the mean. That's about 3 weeks from now. That'll be really relevant to us. Okay, so this other is like mostly style issues. So I'm going to click OK. Again, SPSS is going to pull the output window up to the front. It's going to do the calculation. And it's going to display it for us. So I'm going to do it again so it's up a little higher so we can see it a little bit better. Descriptive statistics, descriptives, and I'm going to say okay. Okay, so here we go. What do we have? Well, we have the number of mothers that are in the study is 800. Number of subjects that have valid information is 800. None of them are missing information. The range is 27. The youngest age is 15. The oldest age is 42. Things have changed, right? The oldest mother in this population of 800 is 42. I'll bet you nowadays the oldest might be in their 50s, right? Easily, right? So at any rate, so you can see how far back this data goes. It's about 20 years old, I think. Okay, so the average age, the middle age was 26.92, right? The standard deviation was 6, and the variance, of course, is that squared, which is 37.299, and so on. So we have some interesting information here, right? It gave us a view of the way that this data is distributed. It didn't give us the mean, it didn't give us a mode, right? There's a lot of statistics that didn't show up here, right? It gives you mean, but it doesn't give you the median. I'm sorry, median. I meant the median, right? It doesn't give you the median, which in some ways, this data, there's a good shot this data might be skewed, right? Because there might be a lot of younger people rather than older people. So the average might not be the best way to describe the middle of this population. Sometimes when the data is skewed, the median gives you a little bit better view of where the middle is, right? Well, how would I know whether this data is skewed or not? What's the easiest way to know whether the data is skewed or not? How about if we get a look at a graph, right? Let's go up here. Let's go up to Analyze, except this time let's go to Graphs, right? I'm an old timer. I'm a legacy, so I'm gonna go to Legacy Dialogues. You could experiment with all the others. That this chart builder and so on and so forth. That kind of works a lot like the some of the drag and drop uh, uh, versions of different graphic programs where you can just drag an axis from one place to another. You can play around with that. I'm just going to go to Legacy Dialogues because I can get it done quickly. And I'm going to go to, let's see, box plot. How about histogram? Let's create a histogram. Okay, so what's the variable that we're looking for histogram? We're looking for a histogram which describes the age of the mothers. So I'm going to click on that and I'm going to move it into the variable view. I can do various other things with it. I can manipulate what it'll appear like a little bit, how it's displayed. But I'm okay with that for now. I just want to get a quick look at this distribution. Now, SPSS, remember how we draw a histogram? We need to break the data up into columns, right, where there's a range, right, say 15 years old to 17 years old. And in there is the frequency of people that are in that age range, and then 17 to 19 and 19 to 22 and so on and so forth, right? We actually want them all the same width. And we want to see how that's distributed, how tall those columns are, and if it's a bell-shaped curve, if it looks like it's normally distributed, or if it's at least symmetrical. Okay, so I'm going to click OK and hope that this produces for us a histogram. Now, who decides how wide those bars are? Right now is SPSS. You have flexibility to tell it to redisplay the data with different bar widths if you want, ranges. Like instead of 17 to 19, you could say years, 17, 18, 19, 20. Or smaller groups, smaller number of bars, but wider, like say 17 to 21, 21 to 25, so on. Right, so you'll have the option to do that eventually. For right now, I'm going to let SPSS decide that. I'll click OK. Did I get a comment there? Oh, okay. Is it okay there? Okay. Okay. So here's our histogram. Right? Does it look like it's skewed? Kind of really funky, right? Yeah, actually, it looks like it's skewed to the right. Right? Looks like we have some outliers there that are older than most of the others. And in fact, in this particular population, that kind of makes sense, doesn't it? Because when this was going on, you didn't get very many women that were having babies at that age, right? For a few reasons. One, physically, and the other, culturally, right? Most people had babies at younger ages, right? So this is skewed a little bit to the right. Okay, and by skewed, we mean that there are values that pull the mean away from the median. Now's a good time to talk about this, I think. Now, imagine this. Imagine you're looking at this data and you're looking at the median. The median and the mean in a perfectly normally distributed population where the values are just higher or lower than the mean just by chance, by random chance, not because there's a difference in how many younger people versus older people that you have, who the youngest is, who the oldest is. But if it's just randomly distributed and it's normally distributed, you would expect the mean and the median, the middle value, the 50th percentile, the middle value, and the average to be the same, and for this to be symmetrical. Okay, so now let's think about what happens if you get an outlier, someone that's much younger when they have a baby, someone that's much older when they have a baby. Well, the median, if it's this person over here, they're still above the middle, so it's not going to affect what the median is, right? But the average is going to be affected by a person who's much older. So the average is going to be pulled to the right while the median stays in the middle, right? So we describe that as saying that it's right or positively skewed, right? So this, because of these guys here, we would say is slightly positively skewed or right skewed. If there were births down here, right, so that it, like all the way down here, well, then we would say that it was negatively skewed. If there's a long tail on the right, on the left rather, we would say left skewed or negatively skewed, because that would pull the mean towards the left or or smaller number. Okay, so that's what we mean by skewed. Okay, now this has multiple modes. You can see here because there's multiple ages where there's a lot more women that are having babies. Okay, so now I'm going to go and take another look at this data from another perspective. That is, I want to get a bit more information. So I'm going to click Analyze. I'm going to click Descriptive Statistics. I'm going to click on Explore in this time instead of Descriptives. Okay, so let's see what's going to happen here. So if I click on Explore, I'm going to again take the age of the mother, right? I'm going to move it in there, and I'm going to go click on Statistics here. Well, this time I don't see a selection for mean, median, mode, and so on and so forth. It's actually going to calculate basically all the descriptive statistics I would ever want. I do see a click mark for confidence interval for the mean. That's getting a little bit beyond where we are right now, but I'm going to leave that clicked for now. That is, I'll mention very briefly when the output window comes up. I'll mention very briefly what that means, but don't get too excited if you don't understand it right now, because we're going to be spending, a lot of time on this, understanding this idea of confidence interval and so on and so forth later on. So I'm going to click continue, and I'm going to let's go into plots. It's automatically now. I know this because I've used the program before. It's automatically going to create a box plot. Remember box plot? That's the one that's vertical with the bars and stuff like that. It's with the feathers and the middle bars and stuff. It's automatically going to create that. So if I want something else, I got to tell it. It's already pre-checked all the time with stem and leaf, which almost no one uses anymore, but it does it automatically. It's by default. It's on when you install it. It's always clicked off. I'm going to click on I'm going to leave it clicked. I'm going to click on just to show you what it is. I'm going to click on histogram as well to create the histogram again, just to show you that it'll do the same thing again. I'm going to click continue, and I'm going to say okay. Okay, and I'm going to just pause for a moment just to take a look at the chat box. Yeah, yeah, Sophia. I think you already saw that, Sophia. That you use them for nominal data. Histograms, numerical data. Bar charts are for nominal data, names basically. Okay, so let's take a look at this. Now, in this case, it summarized the data. It's 800 sample of 800 people. And then it told us the mean, 20, we got the same mean as we got before, but it also gave us the median, the variance, standard deviation, minimum, maximum range, interquartile range. Remember what the interquartile range represents? It represents the difference between the 25th percentile and the 75th percentile. In other words, the width of the age range that represents the middle 50% of ages of mothers. So that's 10. Okay, in fact, you can probably figure it out at some point. You can actually get it to give you the, I'm not going to go through it right now, but you can get it to give you the percentiles themselves as well. Okay, skewness and so on and so forth. Remember we mentioned it was slightly skewed. That can be represented numerically. We'll worry about that as we move forward. So here's a repeat of our histogram. Okay, now this is a stem and leaf plot. You got to remember this program goes back to times when it was very difficult to display graphics on computers. Just text. Computers were just text. The way this works is that it takes a number, like the first digit. This represents the first digit of the age. So this would be a person that's at least 10 years old, and the second digit of their age is 5. So this tells us that there were 5 people that were 15 years old in this plot. This tells us that there were 1, 2, 4, 6, 8, 10, 11 16-year-olds, and I don't know, looks like about 13 17-year-olds. Each one of these represents the second digit, right? And this is how many 18 and 19-year-olds and so on and so forth. If you look at this, if you turn it sideways, if you turn it straight up, it looks very much like the histogram does. It's just a way to display it if you don't have access to a graphical screen, or you're going to print it on a printer that doesn't display graphics. Go back 25, 30 years and you would have had, this would have been valuable to you. Why it does it by default now, I have no idea. Okay, so here's our box plot, which gives us a lot of information also. Okay, the youngest mothers were 15 years old. The oldest mothers were 43 or something like that, right? The median age was 20. Now notice, this is not the mean, this dark bar. This is the median, right? Notice where the median is here. It's not in the middle, is it? It's over here. So remember, this is positively skewed. These older women are pulling the average age away from the median, right? So half of the mothers are here, half of the other mothers are here. So it's skewed to the right. Okay, so this tells you quite a bit, and that 10 came from the 25% of the women are between 15 and 23. 50% of the women are between 23 and 32, and 25% of the women are between. Did I say 50%? That's 50%, and 25% of the women are in this upper quartile, which is between 32 or whatever it is and 43. Okay, so that's how to interpret that. Now, boy, if we're comparing two populations, wouldn't it be nice if we could see the two box plots for the two populations right next to each other? Let's go back to the data. There used to be a guy on I'm trying to Werner Wolf, I think his name was, that did the sports on Channel 7, Eyewitness News, many years ago, and he used to get very excited, very rambunctious, excited guy, and he would talk about a game, and every once in a while his kind of popular phrase was, "Let's go to the videotape." Okay, so let's go to the videotape here and take a look at what we can do with numerical data and this kind of stuff. So I'm going to go back to descriptive statistics. I'm going to go to explore, except this time I'm going to do something a little bit different. Okay, I'm going to take some numerical data, like let's say the weight of the weight of the child in the weight of the infant in ounces. Okay, I'm an old guy. I'm not comfortable with the metric system, so I'm going to go with ounces instead of grams. That's not true. I prefer the metric system, but we're stuck with the English standards system. Okay, so now let's say that I'm interested in whether mothers who were married had a higher birth weight babies than mothers who were unmarried. Right? Well, in order to figure that out, I could just, if I did this now, what's it do for me? It gives me it gives me the birth weight for all babies, right? Notice it's skewed to the left. Those are premature births. You don't get so many high weight births, but you get a lot of premature births. So the average weight is going to be skewed to the left, away from the median, right? So we'd expect the median let's see, the average weight is 116. The median is 118. See how that those premature babies pull the mean downwards negatively away from the median. So the average, the middle weight is 118, but the average weight is 116. Okay, so at any rate, so we see it's skewed. Let's let's see if I know that sniffling that you're doing there with the napkin. That's sympathy, right? That's a sympathetic response. That happens, right? We were just talking about earlier today with a friend of mine. Was talking about a movie called Zelig by Woody Allen. I have all these cultural references people don't get. In this movie Zelig, he's kind of he plays a character who's kind of a chameleon. Supposedly, his life was during the 20s, 30s, and 40s. And wherever he is, he becomes very famous because he seems to turn up everywhere where something's happening. But the unusual thing is that his physical appearance changes. So that he winds up, he has no personality. His physical appearance actually blends in with the people that are, or the activities that are going on around him. If you ever get a chance, it's one of Woody Allen's better films called Zelig. Okay, so now that I've gone off of my usual tangent, let's get back to this. I was just that with so that was kind of a lot of times people cough or have a cold or something like that, and people unconsciously sympathetically kind of sniffle or or if you got an allergy, all of a sudden or yawning, right? Or yawning is a typical example of that. You start yawning, everybody starts yawning. So at any rate, back to this. So I'm going to go over here and I'm going to take a look. I'm going to say analyze. I'm going to go into descriptive statistics. I'm going to go into explore, and I'm looking at the weight of a child. Well, would it be interesting to know if smoking status affected the average birth weight of the infant? Well, in order to do that, I have to break this data. It sounds worse than it really is. Huh? I'm going to stop in about a minute. I'll be okay. I'm going to take a break and get some water. So at any rate, in order to evaluate that, we would need to separate out the mothers who smoked, the birth weight of the babies from mothers who smoked, from the birth weight from the mothers who didn't smoke, and analyze them separately, and then compare the numbers, right? The mean, the median, and so on. So in order to do that, I need to factor those. Factor is kind of like you pull the things apart. Now I said yawn, and we'll look what happened. So at any rate, in order to factor that, I'm going to tell it to break the data or factor the data up into two groups, into the groups which represent mothers who smoked. I don't see it right away, so I'm going to choose marital status instead, which is single and married. Okay, in this particular data set. So in statistics, I'm going to, usual stuff, not going to change anything. Plots, I'm going to stay with what we had. And then I'm going to say, okay, now what do we expect to see here? We expect to see two separate analyses go on here. One for the mothers who smoked, one for mothers who didn't smoke. So I'll click OK. Okay. So here we go. And indeed, look what happened here. This represents, no, I changed it. I changed, right? I decided married versus unmarried. So for married women, the average weight is 119. For non-married women, it's 109. Right? So it looks like there's a difference. We're going to move on later on and try and figure out whether that number is due to chance or it's statistically significant and so on and so forth. For right now, we see differences here in this data. SPSS separated out these two groups for us. And in fact, it makes up two histograms for us. So we can actually kind of see, well, look, how many premature births here and how many here, how was it distributed, and so on and so forth. Stem and leaf plots for each one of them. Let's take a look at the box plots. Right? The box plots show us that the range is about the same. The variability is about the same, but it looks like we can actually see that the median here, or most of the population here, the non-marrieds have lower birth weight babies than the ones who are not married. we can see them side by side. Now, what are all these numbers that are over here? Those are the outliers. SPSS has a formula built into it that it uses to define an outlier. I'm going to take a wild guess now, because I don't remember exactly what it does, but I believe it's 1.5 times the value of one of these quartiles or something like that. 1.5 from when this goes, another half beyond this quartile. So these numbers become outliers, and it puts a number up here. Basically, it's telling you that if you want, I'll exclude these because they seem to be too far from the bulk of the data. There might be something that's an issue with these. And in fact, with premature births, there may be reasons why those occurred, have nothing to do with marital status, right? There may be physical reasons or something like that. So you might not want to include that data when you do an analysis, when you compare these populations. SPSS kind of suggests a way for you to do this, but it's your decision as the analyst to decide whether it's appropriate to remove certain data from here. I have a data set that we'll use later on, which shows the number of, for 1 year, so the number of murders in each state during a period of a year or something like that, during a period of a month. And they actually list 51 states. They list DC as a state. It happened that DC had a very violent month that month. So you had like all these other states with, there's all numbers down here. And then bing, you had DC up here with 37 murders or something like that month. It was clearly an outlier, so different from all the rest of the data. And the idea was we were trying to develop a correlation between maybe level of poverty and murder rate and so on and so forth, or marital status and murder rate and so on. And in that case, might be a good idea to exclude DC because it's so clearly an outlier from the other data. But when we get to correlation and regression, we're going to be talking about that. But this statistic, birth weight, is particularly prone to have outliers at the low end, right? Because it's one thing to have normal babies and babies that are a little bit heavier and stuff like that, but you don't get 40-pound babies, but you do get a lot of premature babies, right? So it's almost, you would almost guess in advance that this data is always going to be skewed negatively because premature births happen quite a bit, right? They're not that uncommon. So this is kind of the nature of the beast here. Okay, so is that pretty interesting, right? That we can actually see this side by side. Okay, so what I'm going to do, I'm going to take a break for about 10 or 15 minutes. I'm going to find something to drink, clear my throat out, and we'll move on from there. So maybe you guys in the meantime can play around with this. When we come back, I'm going to throw it up on the screen here so it's a little bit more comfortable for you guys. Okay, same thing at home. Right, outliers, guys. I just want to remind you that and there's two tabs here, one for lecture and one for lab. They're both for week 2, session 2 or week 2. There's folders for each. I separate them out because kind of this was more lecture material. This was kind of more lab material in this tab, but there's a folder. I think in the future I'm just going to combine them. So you'll see a single sessions tab over here. And if you go in there, all the material will be together, generally in the sequence that I'm going to be presenting it in. So for the time being, that's kind of the way I did it. So just to go back over the lecture tab for tonight in here, we went over data standardization already. I'm leaving it up to you on your own because no way my voice is going to hold out for the whole night. For this discussion or presentation of study types, the study design and inference and so on and so forth. If you click on that, it'll bring you to a YouTube video from a previous semester that is a really good presentation on study design. Okay, so you can look at that on your own. You will be responsible for that material. I'll go over it very briefly next time, maybe something simple question or two will turn up on the homework. But if it does wind up on the exam, it's not going to be real complicated interpretation of study designs, right? But it's something that you should know as you go forward into epidemiology. basic kinds of studies. And the lab section usually is stuff that involves calculations and so on and so forth. That's usually the way I divide it up. Like I said, I'm gonna rethink that and maybe present everything in a single folder sequentially. Okay, so we kind of went over the idea of like how we would use SPSS to display data in tables and graphically. You'll notice that we use the files here. Okay, and I'm going to move on now to something that we're really going to cover mostly next week, but I want to introduce to you because a lot of students find this as a bit of a challenge. Okay, and I'll do a presentation next week, or I'll direct you to one or do one myself. That'll go over a lot of issues that involve understanding probability. Okay, now you guys may remember that probability involved a lot of things, including these things called Venn diagrams, where you have circles overlapping, and this is contained in that, and so on and so forth. I'm going to take a simple look at some problems involving probability to introduce the concept to you, and next week we'll go into it in more depth, and we'll really go into this idea of applying this to understanding how diagnostic tests work. We're going to talk about something called Bayes' rule, and we're going to talk about diagnostic tests. Okay, pretty interesting stuff. Okay, so for starters, I'm going to open up this first file, probability exercise number 1, and we're going to talk about different kinds of data. First thing I want to bring up is when we collect data, there's certain kinds of data that are going to be data that the results of the collection of the data are going to be mutually exclusive. For instance, if I toss a coin, the result has to be either heads or tails. Can't be anything else. And if it's heads, can't be tails. Got it. If it's tails, it's heads. The other thing I'm interested in is whether data is independent. So, for instance, if I flip a coin and I get a result like heads, then I flip a second coin. Well, that second coin has no knowledge of what the first coin was, right? So those samples, those selections are independent of each other. Okay, if I were to go out into a human population and randomly collect data from a population, let's say I wanted to find out what the prevalence of diabetes was in a population, right? I would want to randomly select people from that population. That's not as easy as it sounds, right? Because in New York, how would I do that? I might do that by randomly calling phone numbers, maybe. Maybe that's a possibility. Maybe I would do it by using social security numbers picked out at random by a computer or something like that, and following up with the people whose identities they are, and so on and so forth. But it's not the easiest thing in the world. But in order to evaluate the prevalence of diabetes, I would want to take a random sample. Each sample, each person would be independent of the other person. In other words, if the 500th person I called was diabetic, it wouldn't have any influence on of whether or not the next person was diabetic or not. Now, that's not always the case. Like, for instance, if I were to stop people on the street right now and ask them if they're insured, do you have insurance, right? And I happen to ask the first individual that walked by, do you have insurance? I got two problems with that. It's not really random. Number one, depends on what corner I'm at, right? If I'm on this corner, likelihood of them being of having insurance might be different than if I were down on Wall Street or something like that. The other problem that I have is they may not really be independent from another perspective. Let's say two people, a man and a woman, are walking up the block together, right? Well, if I stop them and ask each one of them if they have insurance, right? Well, you know something, there could be something going on in the background. For instance, perhaps they're married. If they're married, if one of them is working, both of them are insured. So it isn't really it isn't really an independent sample or or it isn't mutually exclusive where if one occurs, it affects no matter if the outcome of one is insured, it doesn't affect the outcome of the other. In this case, it will affect the outcome of the other because it's more likely if they're walking together, they might be married or part of the same family and both have insurance or both not have insurance, as the case may be, right? So we have to be a little careful with that. Okay, and as you go through study designs, you'll notice that understanding this can have quite an impact. Okay, so let's take a look at this. Okay, let's take a look at some. Let's say that these are random samples and uh, 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 truly random samples that we might take. Okay, so let's say that we have the probability that a person is in a particular population is insured is 80%. We're probably pretty close to that now, right? The United States, maybe 80, 85% are insured at this stage in one form or another, at least as long as Obamacare lasts. You choose one person randomly from the population. What's the probability that that person is insured? Prevalence is 80%. Choose one person. What's the probability? 80%, right? Simple enough. Now you choose three people randomly from this population. What's the probability that all three are insured? Let me get my calculator up here. Well, if they're truly independent, right, the probability that the first person is insured is 0.8. Probability that that the second person is insured is 0.8. Probability that the third person is insured is 0.8. The probability that all three people are insured is 0.8 times 0.8 times 0.8. Okay, which is about a little bit better than 50%. Okay. Now, a similar situation might be if I flipped a coin, independent events again. What's the probability that you would get heads if you flip a coin? 50%, right? Okay, what's the probability we get that both flip, that if you flip two coins, that they'd both be heads? It's going to be 50% for the first, 50% for the second, 50.5 times 0.5 is 0.25, or a quarter of the time they'll be both two heads. Well, how about all three are heads? You flip three coins, all three are heads. 0.5 times 0.5 times 0.5. Okay, so now let's take this to the next step. Okay, now let's say I said, I go back to my insurance situation here. Let's say I stop three people on the street, and what's the probability that none of them are insured? Well, in this population, what's the probability of being insured? 0.8. Okay, what's the probability of not being insured? 0.2. So if you stop three people on the street, not on the street, but you randomly select three people, what's the probability all three of them will not be insured? 0.3 times 0.3, 0.2 times 0.2 times 0.2, right? Which is 0.04 times 0.2 is 0.008, right? Little, I think, right? I'm not going to bother, but you get the idea, right? So it's the inverse. 1 minus the prevalence is the likelihood that it would be unemployed. Now, this was a pretty simple thing to figure out because I made it so that you only have one possible outcome. Everybody's insured, everybody's uninsured. I could do it for 8 people. What's probably 8 people, or you put 8 people and they're all insured. It's going to be 0.8 times 0.8 times 0.8 times 0.8 times 0.8 times 0.8 0.8. That's great. Easy enough to calculate. What if I asked you now, what's the probability that 3 out of 8 are insured? Oh, well, things get a little bit more complicated now because I'm picking out 8 people, right? Let's say it's the first person. What's probably they're insured? Well, 0.8. Well, I only need 3 people to be insured, right? So I can meet that criteria either by having the first 3 people insured and none of the others, or I could have the first, third, and fifth and none of the others, or the middle 3. Or there's many different ways, not a million obviously, but we could actually calculate the number of ways there are for us to satisfy that criteria, right? But it's a lot more complicated than 0.8 times 0.8 times 0.8. So we're going to keep that in mind. Okay. Yeah, exactly. Factorial. Good. Perfect. Okay. We're going to get into that along with the Venn diagrams next week. And then we're going to get into, everybody smiles when they hear that. We'll get into that more next week, along with the diagnostic testing. Okay, but for right now, we're going to take a relatively simple look at this. Okay, so now, what's the probability of choosing 3 people? We just went through that, basically. Okay, fine, 75%. Okay, now I'm going to ask you a tricky question here. What's the probability? Let's say you choose a people around. You repeat your sample of 3 people 1,000 times. Okay, well, first of all, number one, I just decided that what's the probability that all 3 people would be insured was about 50%, right? If I pick 3 people out randomly, it's 50%, right? Now, what if I said to myself, I'm going to take a sample of 3 people many times, right? So I'm going to do it 1,000 times. That's basically a lot. That's basically infinity as far as statistics is concerned. That sample of 1,000. That's a lot of people, lot of samples. I'm going to take a sample of 3 people 1,000 times, and you find that 75% of the time that 3 people were insured. Now, knowing that 80% of the population is insured, the prevalence of insurance is 80%. What would that tell you about your sample? What would you expect to get the average number of times that you get 3 people insured? What would you expect to get if the prevalence is 80%? You would expect to get, remember we calculated that. You would expect 50% of the time you would get 3 people insured if you picked out 3 people randomly, and you would expect all 3 of them to be insured 51% of the time actually. But when you actually did it 1,000 times, the average came out to be 75%. What does that suggest about your sample? It's not really random or independent, right? You would expect to get an outcome that's close to, because it's such a big sample, you would get an output that's close to 50% of the time getting all 3. Your theoretical result of 51% would be pretty close to what you would get in practice when you take a big enough sample, right? So that would suggest that there was a problem with your sample. Okay, so let's take a look at how we might predict these more complicated situations where you're interested in what percentage of people, what the outcomes might be if you're not looking at all one way or all another way. So I'm going to open up the next file. Okay, and I'm going to create something called a probability tree. Okay, I'm going to use my tablet for this so I can write. Okay, hope you guys online are still there now. And then you came back with me. Didn't give up on us. Let's see which one of these. Yeah, we got blank ones here. Okay, good. Okay, coin is tossed 3 times in succession. We're going to create a probability tree that represents all the possible outcomes for 3 coins being tossed in a row. So I'm going to do that here. Okay, so we can do this without getting too sloppy. Something's not happy. Uh-oh. I think I might be out of luck here. I might have to do this the hard way. My cable's a little unhappy here. Oh, yeah, but let's turn this on. It will work now. Nope, still doesn't work. Okay, I'm gonna have to do this the hard way. Okay, so I'm going to do it this way. It's going to look a little ugly, but it'll still work. Oh, good. Thank you very much, April. I appreciate that. Just let me know she's still there. Okay, so I'm going to toss the first coin. When I toss the first coin, right, the probability, here we are, his first coin toss. I got two chances here. One, it's either heads or it's tails. And it's going to really slow me down. Heads or tails. Those are the only two possibilities. Probability it's heads is 0.5, and the probability it's tails is 0.5. Okay, so let's say it comes up heads. I'm going to flip it again. Let's say it comes up heads. The second toss is going to have two possibilities again. It's either going to be heads or it's going to be tails. Actually, I'm going to put heads up here again. Make it a little bit easier. Or it's going to be tails. Again, 0.5 and 0.5. If it had come up tails, similarly, it could either be heads or, I'm not going to bother to write the 0.5 again, or tails. Now, I have four possible paths here now at this stage. I could have tossed a head and then another head. I could have tossed a head, then a tail. I could have tossed a tail, then a head. I could have tossed a tail and a tail. These are all independent events, so one doesn't affect the other. The last coin, I'm going to toss it again. Could be a heads for this outcome. Could be a tails for this outcome. For this outcome, could be a head. Could be a tail. For this outcome, could also be head and tail. And again, head and tail. Okay, so now let's look at all the different possibilities here, right? Could be first going head, tail, head. Head, tail, tail. All of these are 50%. All of these have 50% chance. Okay, so let's look at what's the probability of getting all three heads. Remember we said that was 0.5 times 0.5 times 0.5. Well, indeed, 0.5 times 0.5 times 0.5 is 0.125. Right? For you guys that are a little bit more comfortable with numbers, you know that's 1 out of 8. Probability of getting heads is 1 over 2 times 1 over 2 times 1 over 2 is 1 over 8, 0.125, 1/8. Okay, now the next possibility is heads, heads, tails. Well, what's the probability of that? That's prob 0.125, right? So what's the probability of heads, tails, heads? 0.125. Or what's the probability of getting a head, second coin, tails, third coin? It's 0.125. Okay, I'll try and go through this quickly. Tails, heads, heads, 0.125. Tails, heads, tails is 0.125. Tails, tails, heads, 0.125. Right, they're all the same really because it's because they have 50%. We're going to see that it can be different in other cases. Tails, tails, tails probability is 0.125. Now take a wild guess. We've exhausted every possible combination. What do you think those add up to?
1.
Exactly. Every possibility is included here. Right? Every possible sets of outcomes included here, it adds up to 1, which is all possibilities. Now, what's the probability of getting all three heads? Well, we said heads, that's 0.125. Doesn't happen any other way. How about all tails? 0.125. What's the probability of getting 2 heads and 1 tail? Oh, well, there's a few ways that can happen. Heads, let's see, heads, tails, heads. So this would qualify, right, for 2 heads. Heads, heads, tails. This would qualify, right? And let's see, where else have we got it? Tails, heads, heads. This would qualify. So there's 3 ways to get that outcome. So what's the probability of getting 2 heads and 1 tail? It's going to be 0.375, right? Okay, I'll do that again. Should I do that again? It's kind of hard to see here because I'm stuck writing with my mouse. Oh, that's a good question. I'm going to be showing you next week. I'm going to be showing you a formula which uses factorials and other ugly things that will help you calculate this other ways. But intuitively, I want you to just look at this intuitively for now. Where these numbers are coming from. What's coming from is a number of possible ways to get equally likely outcomes.
So it's 1.25 plus 1.25 plus 1.25.
Yeah,
That's how you get 0.375?
That's how I got 0.375. Because those are the three outcomes, the three paths on this tree that would give me two heads and a tail. Let's follow tails now. Tails, tails, heads. That's one way I can get two tails, right? That's this one over here. I'm going to make it darker. How about any other ways? Tails, heads, tails. This one, right? Let's see if there's any other way. Well, no more over here because that's tails, heads, heads on the other. How about over here? Heads, tails, tails. This one over here. There are three ways. Notice by now I've circled everything, so I've counted for all the possibilities. 0.375, right? So if I asked you what's the probability of getting two tails, if flipping tree coins get two tails, you would say 0.375. Now, what if I told you, let's do the same thing now for 10 coins? Well, first of all, we need 80 pieces of paper. We'd be using the floor, chalk, whatever, because can you imagine what that tree is going to look like by the time we get to 10, right? It's going to be ridiculous. So you wouldn't want to do that. You would want to apply some formulas that would help you calculate this, right? We'll worry about that for next week. But this is the idea. The idea that we can calculate these probabilities. We can understand where these probabilities can come from. Here's one that's a little bit more complicated, but we're using a tree to solve it again. Now you've been in this situation. I know I have personally been in this situation as a student. The student randomly chooses, let's say you got three multiple choice questions on an exam, and you have no clue what the answers are, right? So what you do is you're going to randomly choose three choices, right, with options A through E. In fact, I could tell that there were five possible choices with only one right answer. Why could I tell that? Because if I look over here, this is the first question. You have a 20% chance of getting it right and a 80% chance of getting it wrong. Why is that? Because you're doing it randomly. You don't know anything about it at all. And that would suggest that there are five choices and only one of them is right. So 20%, 1 out of 5 is 20%, and 4 out of 5 is 80%. So you have two possibilities here: getting it correct or getting it wrong. That first question. Now, what's the probability that you would get all three correct? Well, it's going to be 0.2 times 0.2 times 0.2, which is equal to 0.08, right? Well, what's the probability of getting them all wrong? That's a bit better. 0.8 times 0.8, 0.8, coincidentally the same as we were looking at with the insurance, which is 0.512, right? Well, what's the probability of getting two right and one wrong, or two wrong and one right? Well, that's a lot of ways that can happen, just like with our coin, except that instead of being a 50% probability, let's look at how we could get two right and one wrong. Two right is 0.2, 0.2, and one wrong is 0.8. So the probability of following this path is 0.2 times 0.2 times 0.8 is 0.032, 3.2%, right? Is there another way to get to that same point? Well, yeah, there is. You get the first one right, second one wrong, third one right. That'd be 2, right? And that's going to be 0.2 times 0.8 times 0.2 is 0.32. Okay, well, any other? No, this is 2 wrong. You can't. We can't go up this direction and find that. Now let's go this direction. Wrong, right, right. That would give us 2, right? And that's 0.32. And wrong, right? That doesn't work. Wrong, right? That doesn't work there either, right? So let's add up all the possible outcomes where I could get 2 right. Here's one. Here's another. And here's another. There's 3 of them. So it's 0.32 plus 0.32 plus 0.32. So it's roughly 10% of the time you would get all 3 right. Right? We'd add them together. If I added up all these possibilities, what would I get? I'd get 1, right? Or 100% of the time. Okay? So this is we're gonna look at this from a lot of different perspectives. Next week, I'm gonna kind of kill it right here so that we can go back. Well, let me see what else I got here first. Yeah, I want to hold off on that for next week. Next week, we're going to take we're going to go back over this and take a look at some of the formulas that are involved. And then we're going to start to look at diagnostic tests. And I'll give you an example of diagnostic test. You can preview this stuff if you want and take a look at it. This is really material from week 3 that we're starting to look at now anyway. Okay, so for instance, when you go and take a diagnostic test, there's probabilities involved there. Yeah, I'm trying to think of something that is around now. I'm going to go back about 20 years to the a little bit more than 20 years. Yeah, quite a bit more than 20 years now that I think about, to the mid 80s. In the mid 80s, when the HIV epidemic was just starting, they had 2 tests. They had a relatively quick blood test that could be done in a doctor's office, and they had a more accurate gold standard test that took a couple of weeks to get a result on. They're very expensive, very elaborate, took a long time to get a result. And of course, you had to wait for that test for 2 weeks, which is, like ages, if you're concerned about whether you're HIV positive or not. So a lot of doctors relied on kind of a clearance test, right? And this was a test that would give you a pretty quick result, but it wasn't as accurate, right? So now, let's say you take this quick test, and you take this quick test and you get a positive result. Well, what's the first thing you're thinking when you get a positive result, right? What's that? That you're HIV positive, right? That's not true, though, right? Let's think about that. What do they use for screening men for prostate cancer? Use PSA. Huh? Yeah, PSA, protein specific antigen or something like that. Use a PSA. If you're over 4, they start to get worried, right? If you have PSA, how accurate is that test? So if you have a PSA over 4, how likely it is that you actually have cancer? Not very likely at all, right? In other words, the predictive value of that test is not great. They have to then go do other things, and some of those other things are pretty invasive. So it's not a great test. What about breast exams? Well, breast exams, right? How many of you know women that have positive results on breast exams that biopsied and have cancer, right? So the screening is a diagnostic technique, right? Oh, you're positive. We found a growth or a lump or something like that. Now we have to test it further, use a gold standard. We have to biopsy it, right? But that's a screening technique. How about Pap smears, right? Many Pap smears that are positive turn out not to be cancer. So the problem with diagnostic tests is how accurate are they? How predictive are they? So there's 2 kinds of predictive that we want. One is you want that test to tell you if you have the disease, right? So you want that screening test to be accurate and let you know and be as accurate as possible and say that if you have the disease, we're going to catch it with that screening test. You also want that test to not tell you that you have the disease when you don't have the disease. You don't want it to be a positive test when you don't have the disease, because it could lead to more invasive testing and so on and so forth, and treatment that you don't need and so on. Right? So that's one of your concerns. So when you get a positive test, you want to say to yourself, now that I have this positive test, what's the probability that I really have the disease? That's something called the positive predictive value. And on some tests, that might be 90%. Oh, your screen came out positive, we're 90%. We're going to go on, and 90% of the time, people that have this result actually have the disease. Right? What does that mean? That means 10% of the time, it's a false positive. They don't have the disease. Sometimes that predictive value can be very low, surprisingly low, especially diseases that have a low prevalence in the population. They're rare because you test everybody, right? So if the test is only 90% accurate, since very few people have the disease, you're going to have a lot of false positives. Okay, and similarly with negatives, you want to make sure that if you have a negative test, that you really don't have the disease. That's negative predictive value. Next week, we're going to take a closer look at probability, and we're going to take a closer look at how diagnostic tests work, and we're going to learn how to calculate different ways. We're going to learn how to calculate information about the predictability of these diagnostic tests, including something called specificity, how good they are at like screening positives, catching positives, sensitivity, how good they are at accurately telling people that are negative that they're negative, and predictive value. If you test positive or negative, what it means to you in terms of how accurate that test is or how likely that you really have the disease. So really interesting stuff, and it's all probability based. We're going to figure that stuff out next week. Okay, so you guys next week online. You have a reason to come in and visit me here. Okay, and we're going to be doing some pretty interesting stuff with the diagnostic tests. I'm going to scare you with a little bit of math when we talk about the formulas that are involved in calculating, the factorials and so on and so forth. Scare you with a little bit of math, but a lot of that is not something that we're going to use in application. We're going to find other ways to use tools like Excel and SPSS to do a lot of the calculations for us.
I have a question, Professor Camilo. On the assignment one data files, are those, I see the quiz is up.
Yeah.
Are those data files our exercises?
Yeah. Well, if you go into the assignment, in the assignment it'll ask you to do certain things that involve data files. So, for instance, it'll ask you to do some calculations with Excel, and there's an Excel, those files include that Excel file, and it'll ask you to do something with SPSS. Yeah, I'll open it. Yeah, I'll open it right now so we can take a look at it together. I'm going to go into assignments just to make sure it's not that confusing. Here's assignment 1. I'm going to open it up. Yeah, same thing. SPSS calls it quizzes, but it's really an assignment. Okay, I'm going to click continue, and it's going to ask you to tell me which of the following category are categorical variables. And then the next one, and it gives you a hint. There's 2 correct answers there. Okay, which of the following are discrete numerical variables? I'm sorry about that. I don't even like dealing with discrete, just numerical variables. Which of the following are so on and so forth. And as you get further down, for instance, using the data provided in the student test scores Excel file, use Excel to do something. That's what those extra files are for, right? They're involved. You need them to answer the questions. And in this case, it means doing an Excel calculation and uploading the result, your file, to me, or doing an SPSS calculation, copying the chart to a Word document, and then uploading the Word document.
It says attach, right?
Yeah.
Attach file.
Yeah, attach file. It's there somewhere.
So we will have to upload.
Browse my
See,
yeah.
I wasn't planning to upload SPSS to my home